Hi, my name is Rafael. I'm from DTU Energy, and today I have a pleasure to introduce you to how to model electrolysis systems. So, what I would like to do this today is to give you some brief overview of what the electrolysis system looks like. Because you may already know a little bit about the technology itself, but sometimes we don't talk about what is necessary to have around that technology to make it work. So here I try to show a diagram of these main auxiliary systems that we need to supply our electrolysis stack with the necessary requirements that we need to produce hydrogen. So for instance, in order to produce hydrogen, we need water, but this water needs to be clean and removed from the impurities. So usually we have a first step of water treatment to remove this and to assure that no impurities will be on our equipment. And besides that, we also need to control the temperature because some technologies are endothermic, some technologies exothermic, so the temperature is very crucial to keep the system operating as designed. Therefore, the thermal management system, auxiliary system, helps on providing the heat necessary or to releasing the heat to keep the stack working at the conditions that we want to. Of course, the electrolysis stack uses electricity to convert water into hydrogen, and this electricity is in DC form, DC current. So we need to convert our AC current from the grid to the DC current that is necessary to run the electrolysis stack. Therefore, we need some auxiliaries, power electronics, to do this conversion. After we produce the hydrogen, this hydrogen is not pure. It will have some impurities of water and oxygen that we really don't need or don't want in our pure hydrogen downstream. So we have some systems to purify this hydrogen, removing the oxygen and the water, so that we can compress the hydrogen for the needs that we want. Maybe it's the storage, maybe it's another conversion. So, of course, the system it's different depending on which technology you're talking about. And we have three main technologies: alkaline, PEM, and SOEC. And here I would like to show you, for instance, one example of alkaline electrolysis system. And in here, we have all that steps that I described before, but in a particular way. So you can see that the water supply, it's treated to get part of the recirculation electrolyte in the alkaline system. This recirculation has also a cooling system imbued to keep that temperature as we want. The oxygen and the hydrogen are then separated in different vessels, and the hydrogen, that's what we are interested on, goes through steps on separation of water, removing of oxygen, and removing the minor water vapor that we have there, because we want to compress this to some process downstream. And the less water that we have, the better the efficiency it is of this downstream process. So as you can see here, this is the alkaline, how it will look like a generical system for alkaline systems. Of course, it changes from manufacturer to manufacturer how these equipments or the technologies for each one of these steps is chosen. For instance, a dryer may be different from a different manufacturer that we have here described. Similarly, we can also look at the PEM electrolysis. And you can see that it's very similar to the alkaline, but it has also some crucial differences. For instance, there is no recirculation pump on this side of the hydrogen, and the hydrogen and the oxygen usually work on different pressure levels. That means that we have sometimes not even a compression step afterwards, because the hydrogen is already produced at high pressure that we may be able to use. Nonetheless, we still need to remove any oxygen that may have pass it through one of the sides to the other, to the hydrogen side, and we also need to remove any water vapor that is still there. Finally, the SOEC is a bit different from these other technologies because the SOEC is a high-temperature electrolysis system. So, as you can see here, what is the main difference is that we have, for instance, an evaporator. So this will consume heat or power to produce steam that will be used to generate our hydrogen. And that has its pros and cons, as you may already know, that you can, instead of using electricity, you can use a little bit of heat from another process or another source. The other side, you also have an oxygen or air recirculation, and you have these heat exchangers here to try to save as much as energy that you have and to avoid you having to expend extra energy on heating up these reactants. So, of course, it's really nice to have an overview, but sometimes we need to know a little bit how much actual electricity do we need to produce this hydrogen. So, one of the main things that we want on analyzing the system of electrolysis is to really pinpoint how much energy do we need to produce this hydrogen. And traditionally, we would approach the hydrogen production as we would approach any other process, chemical process. So it's very common for using, for instance, commercial process simulations like Aspen Plus or Aspen HYSYS, or if you are more interested into the dynamics of the system, maybe using MATLAB, Simulink, and Modelica, for instance. They're very popular frameworks, softwares to develop your model for that strict requirements on the industry or research. And most of these commercial softwares already have some kind of pre-built-in models. For instance, here on your left, you can see the model that Aspen Plus provides from his own software, and it's very detailed with all the heat exchangers and phase separation. On the other side here, you have a PEM electrolysis built from Simulink framework, and it is also very detailed to having the heat exchangers and some details of the membrane and the stack design, especially the thermal mass of the stack to see how the temperature will evolve with time. However, of course, modeling in these softwares requires some knowledge of the software and also a lot of maybe inputs and data. So what I would like to show is maybe a simplify, because maybe you need to have some quick numbers or you need to calculate some quick numbers for the system, and you will wonder how to do it. So what we can do is actually pinpoint from all that steps that I put before, we try to find what is the main consumers and how to estimate the electricity from that main consumers. For instance, the electrolysis stack, if we derivate how much is the power, the equations of power, and the equations for the hydrogen production, we can come up with this simple equation here, which looks like has a lot of terms, but actually what it has is just the number of electrons that you transfer on this reaction, the Faraday constant, the molar mass of the hydrogen, and here are actually the specific, I would say, all these things are constants. They are thermodynamic constants, so you don't need to actually get the numbers, but the specifics of each technology, and maybe even each manufacturer, comes with the voltage cell, so how the voltage it is for that cell on the stack, and the Faraday efficiency, also known as current efficient, which kind of gives you an indication of how much of that electrons that you exchange on the stack really turns into hydrogen. And if you know these two numbers, you can try to make some kind of put in this equation to give an indication of how much energy, electricity you need for every kilogram of hydrogen that you want to produce. And I did here an example, for instance, on the state of the art of this voltage of these main technologies, and also the Faraday efficiency of these technologies. Usually these low temperature technologies have a lower Faraday efficiencies than the high temperature one. And you can see that the voltage and the Faraday efficiency greatly impacts on the electricity consumed to produce the hydrogen. This is the main consumption that we have on the system itself, is the stack. However, it's not the only one. Also, most of the times, the voltage of the cell, because the manufacturers will provide you this number. So you also can use some data sheets from the manufacturers to come up with this number. And you're going to see that they are more or less close to these ones that I put here. But of course, each manufacturer can design the stack to operate on a different voltage level and therefore have slightly different changes because of the trade-offs between technical and economical aspects of the design of the stack. So this would be the electricity consumption that you would get just by looking the stack itself. But what about the system? And then we see that one of the main actual consumptions is connected to the transformers and the rectifiers. So to convert the AC to DC energy current, you actually lose a lot of electricity because the efficiency of this conversion is usually 95%. It's getting better, but at the moment it's 95. So if you use as a reference, for instance, the power of the stack, the consumption, and use here on this equation, for instance, to know how much would be consumed in the power electronics, you're going to see that a considerable amount of energy, it is extra expended on trying to convert that AC to DC electricity. So a lot of research is going to the power electronics to make it more efficient, more cost efficient. Related to the thermal management, most of this low temperature electrolysis, they would require some cooling. However, they are very little compared to the high temperature electrolysis in comparison. And the high temperature electrolysis, of course, it's a bit difficult to estimate how much electricity you would consume or energy you consume to produce the steam because of the energy integration. So it could be that the manufacturer has a so nice heat integration design that it saves some energy. However, most of the times you have to provide the evaporation of the steam as a whole. So as a safe or maybe conservative assumption, you could estimate how much energy it is based on how much on the enthalpy of evaporation of that steam. So basically, this equation, it's trying to calculate how much water per molecule of hydrogen that you need. So this comes from the stoichiometric. And then there is a few feedstock utilization efficiency, because not all steam is converted on the stack, especially on the SOEC. Usually it's at 75%. So you have to increase a little bit more steam than you actually convert on the stack. And finally, you can multiply by how much energy does it take to produce that steam to have an indication of how much energy will consume to produce that steam. So here is like an example, so some very state-of-the-art, I would say, numbers for fuel utilization, 75%. And here it's from thermodynamics textbooks. And I'm assuming that the steam will be supplied at 2 bar. And you can see that it's a lot, or it's a significant amount. And that's kind of how the SOEC differs from the other technologies, that you have this preeminence of the heat, the importance of the heat. And we'll later see how this will impact the whole figure. But as I mentioned, as a rough estimation, you can try to estimate how much heat will be required based on the steam consumption. Finally, you also can see the drying. And the drying, it's a bit difficult to estimate because it depends on the technology that you choose. So here, for instance, I'm using some numbers from the literature that tries to correlate how much energy you need to to dry the hydrogen based on the efficiency of this dryer and how much heat it requires to dry that hydrogen. All the technologies need that drying, so they will probably much use the same technology. So there's not much difference between each technology, and as you can see, it adds up a little bit of electricity to make that hydrogen dry. But it doesn't differ between the technologies. What it differs between the technologies is the compression. And of course, the hydrogen compression differs because some of these technologies operate at a high pressure, while most of the alkaline and the SOEC operates at atmospheric pressure. Therefore, if I want to reach a same pressure level of 30 bars, I will need different amount of electricity to reach to that level. And you can try to estimate this by using some classical thermodynamics equations. This is one of these equations. It's a little bit adapted to our needs, but it basically derives from the isentropic process of compression. And there are some efficiency factors to account with these losses on imperfections of the equipment, imperfections of the process. Most of these parameters are constant, but what is not constant is this pressure level difference that ends up in this equation here. So the higher the pressure difference, the higher the compression. And as you can see here, that the PEM electrolysis requires far less electricity than the alkaline and the SOEC because of this high pressure that is producing already on the stack. So this is a great advantage of the PEM compared to the others because it not only saves electricity, but it also saves cost of not having a compressor step to make the hydrogen available for the process. This appears also, as you can see here on this term N. And N is the number of stages. So if you are pressurizing from 1 to 30 bar, you need at least 3 stages of compression to avoid the gas to reach high temperatures and be dangerous. While if you're just having this going to 20 to 30, you only need a single step. And this means that you only need maybe 1 compressor instead of 3 compressors on the others. So this is also a savings in cost. Usually the water treatment is not the process that consumes more electricity. And just to give a perspective, I put here, for instance, how much would require of electricity if we wanted to desalinate water from the ocean to use actually in our process of electrolysis. And using some kind of key numbers from the literature, we can see that for every one of the technologies, the consumption is far less than the other process that we just estimated. So usually it's not a bottleneck, the water treatment as a power consumption, as electricity consumption. It may be a bottleneck if you don't have water available. So, but this is because of the cost of the water or the availability of the water, not because of the energy requirements. Right. In order to estimate our system consumption, we can sum all these contributions that we enumerated to have a rough approximation of how much electricity we really need to produce that hydrogen for process or for applications. And if we are interested to evaluate the efficiency, we just need to compare this number that we are estimating here with the lower heating value of the hydrogen. And this will give us the efficiency at the lower heating value. So if we try to compile that numbers that we just estimated before, we would see this picture. So the alkaline, the PEM, and the solid oxide electrolysis. And what you can see is that it does have some difference between the stack and the whole system. As you can see, these other colors here are the system contributions to the power consumption, especially for the high temperature electrolysis, because you have this heating contribution that may be power, may be heat for another process, but nonetheless, it's a big chunk of the how much electricity or energy requires your process. Also, you can see that, if you only compare the stacks on the PEM with the stack on the alkaline, the PEM looks much far worse. But once you take into consideration that you don't need to compress the PEM compared to the alkaline, you see that they look much more close, the numbers. And the efficiency also look closely. So that's what is important to also not only look to the stack, your reactor, but also the other requirements that you have around. Because this can change, of course, the picture of how much energy you require and how much it will cost to you as well, because electricity usually is one of the main drivers of this green hydrogen production. What we see today was a little bit about the auxiliary systems that we need to produce hydrogen, and they are connected to either like making the water as we want or making the hydrogen as we want. And of course, keeping the conditions of the stack as we design. After that, we had a brief introduction of some of the tools available for modeling that. For instance, process simulation in Aspen HYSYS or Plus, or some dynamic simulations using MATLAB, Simulink, or Modelica. And finally, we try to wrap it up by showing you what the simplified calculation of the systems will look like to show you how much we are talking about of this difference between the equipment and the system, and how much this affects on the overall picture of the different technologies. I hope you like, and thanks for your attention.